You got to get a thick hide. I mean, you can't let stuff bother you. Okay, going to start in with chapter 7. So, here we go. We've got everything you need to know now. Okay, we've been talking about the math associated with converting things, grams to moles. We've talked about how to name things, how to use the periodic table. Now, I promise you none of that is going away. Okay, so if you think it is, you're largely mistaken. So you've got to stay up on this, because now what we are going to do is take what we know and further progress and get into chemical reactions. Writing chemical equations, look at the different types of chemical reactions that exist, how to classify them, how to know what's going to happen when you mix two things together, how to write that out, to communicate that to someone. So there's a lot of stuff to cover here, but not too bad. Here's what we know. You've probably picked this up by what I've said thus far, but here we're going to actually define it. We know that on the left, the way a chemical reaction is written is generally there's whatever you mix together, we put on the left side. Okay? For right now, things change later on in more advanced chemistry, but we'll stick with the basics. The left side of the equation, we're going to say that since those are the things that are reacting, we're going to call those the reactants. And on the right side, since those are the things that are produced from that reaction, we call those the products. Okay? So just like in an automobile engine, okay, your reactants would be, at the most simplest level, octane, which is only really one part of gasoline, but the most important part, I suppose, and oxygen. Those two things together, when they react, produce these two things. Okay? They combust, and they produce carbon dioxide and water. Now, you'll notice something, is all the atoms that you see over here, not necessarily the number, but the types. Okay? You see these black spheres here that are all stuck together are actually carbon atoms. These white balls represent hydrogen atoms, and here's two oxygen atoms stuck together. You'll notice that on the other side of the equation, what you do is basically take, if this was a deck of cards, you still have the same cards, you just reshuffle them, is what you do. So on the other side of the equation, you're still going to see those same atoms, but you may see them in a different combination. Like over here, notice that the carbon was not attached to any oxygens on the reactant side, but after everything mixed together, there was some sort of reaction that drew the carbon and the oxygen together to form carbon dioxide. And you'll see that the oxygens pulled off some of these hydrogens to make water. Now what you will see is the picture that, as shown right here, does not reflect the law of conservation, right? On the left side, you've got 8 carbons and only 1 over here. So what does that mean? That would mean that a little bit later, as you will see, that more than 1 carbon dioxide will be produced as a result of this reaction, and more than 1 oxygen will have to be put into this reaction to balance out everything. Okay? But individually speaking, the molecules that are present, this is what you would see. Okay. So there's a little definition. You can read through that as far as what reactions are. Okay, you've got matter. You mix a different couple types of matter together, and you get a new different type of matter. That doesn't mean you've created and destroyed atoms. That means you've reshuffled the deck, and you've got a different classification of matter now, a different type of matter. Okay, so you're rearranging is all you're doing. You're not. Realize this too. When I say elements are not transmuted during a reaction, I mean they do not fade away and turn into another element. Now, in Chem 2, we talk about radiochemistry and nuclear chemistry, radioactivity, that kind of stuff. And in that case, sometimes atoms actually start to lose parts of themselves. They start to degrade, and they release that energy, and that's what radiation is. Not in this class. Realize that we do not have, in a chemical actual reaction, when I mix this with this and I get a product from that, I'm not taking a sodium atom and a chlorine atom, putting them together, and changing the sodium atom itself into something different. It's still a sodium atom. It's just been stuck somewhere else. Okay? Okay, some basic evidence that a chemical reaction has taken place. What things can you look for? Now, with the precipitate lab, you've got a good idea of some basics. Okay? For example, a precipitate itself. If you mix two things together, like when you took lead-2 nitrate and you mixed it with potassium iodide, you might remember what happened. Yellow precipitate. That was the lead-2 iodide that formed. Okay? That's obviously an indication that a reaction occurred. Two things were clear, you put them together, not clear anymore. Okay? So there's a lot of things you can look for. What happened whenever you took sodium hydrogen carbonate and reacted it with, I don't know what acid we used, hydrochloric acid, it bubbled, right? That could be some sort of sign that a chemical reaction took place. There's some other things that you can do. You would have seen had you have done the lab that we skipped. One of the things that we had to do in that lab was to take magnesium ribbon, react it with oxygen, and the way that you react something with oxygen is to light a flame, okay, give it a lot of heat underneath it so that the oxygen molecules right around it in the atmosphere can start, because of that heat, get catalyzed and start to react with that magnesium. You would see that magnesium looks like it was, quote, burning. It's not. Burning itself is just a reaction with oxygen, when something violently reacts with oxygen. And that magnesium would start to glow very, very bright white. Okay, sort of like actually, if you think back to Westerns, remember those guys that had the camera and the flash pan and they had the thing over their head and they were holding it? That was actually magnesium powder that was in that. It was a really bright white flash that would happen whenever these things burn. Magnesium burns. But anyways, the release of heat, the release of light, all these things could be indicative of a chemical reaction. So, you got visual clues. A permanent change whenever associated with a new thing that forms. Okay, color change, precipitate, gas bubbles, large energy changes. In other words, if you're holding something, for example, if you take magnesium hydroxide, or magnesium sulfate, Epsom salt, and put it into water and make a solution of like Epsom salt and water, you'll feel it get really cool. You'll feel the container get really cool. That's an endothermic reaction. It actually sucks in energy from the environment, and in so doing, when you're I'll discuss this, it'll freak you out a little bit later, in terms of what heat actually is, and there's no such thing as like cold movement. Okay, cold air doesn't really, there's no such thing as like a cold air movement. It's actually warm air moving away from a situation that leaves with the perception of cold. Yeah, I'll explain it later. But anyways, if light is given off, if something becomes very hot or cold to the touch, then you know a chemical reaction has occurred. A new odor, something smells different. A whooshing sound from a test tube, that's always a good sign. Permanent new state, something that you can't change. A different taste, probably that's not one you want to explore in this class. All these things, these seem obvious. Now, on your slides, this slide gets pretty messy because there's a bunch of pictures that overlay other pictures, so you may not be able to see them all. But the first one on there is like, there's an example of a color change. It's kind of cool how that happens if you really think about it. That when you're starting with, let's say this was like silver nitrate and this was sodium chloride, what would that precipitate be? Do you remember? If I was mixing silver nitrate and sodium chloride, what might my precipitate be? Silver chloride. That's right, silver chloride. So if I was bringing in sodium atoms and chloride ions right there, and I had silver ions and nitrate ions floating in here, when I put them together, the silver and the chloride can come together, and when they do, instantly you see that precipitate start to form. So that would be indicative of a reaction. A gas, we will later on take like some calcium. We won't ever take like sodium or potassium and drop it in water because it would explode. Actually, it's kind of cool if you take little shavings. If you took a big lump, it would just explode. But if you take little tiny pieces and get it like a big bowl of water and take like a little piece of sodium and drop it in water, it's really cool because it starts to shoot off sparks a little bit, and it starts to skips all around and jumps all around the bowl of water. It's pretty neat. But anyways, emission of light. You've seen those like camping sticks, right? Those glow sticks. They don't really get hot whenever you use them, but they do emit light. I'll discuss in a later chapter when we talk about electron configurations on certain atoms, how light is emitted from atoms. We'll get into some philosophical kind of stuff. It gets kind of crazy. But there's burning magnesium. There's a lot of smoke over that one, but it's actually a very bright white light. So that would be a release or absorption of heat, for example. Now, in a previous chapter, we talked about chemical versus physical changes. And you could sort of identify whether or not something was a physical or chemical change based upon, are the molecules different from when they started? For example, is boiling water a chemical change? Yes or no? No, it's not. Because either way, it's still water. All that you've done is change the state of the water. You've changed it from a liquid to a gas. Okay, so that is not a chemical change. Now the thing is, though, to be absolutely sure that a chemical change has taken place, what you have to do as a chemist or a chemistry student, at least, is to analyze what's going on at a molecular level. Okay? To be sure, like for example, when you crank up the heat on a pot of boiling water, there's some steam. You can see it, right? You see some fumes leaving. That's actually not fumes. It's vaporized water molecules. You see that leaving. You feel heat. You feel all this kind of stuff, which are all things that could be indicative of a chemical change. So how do you know then that it's not a chemical change and that it's a physical change? Well, you really have to consider it at a molecular level. You've got to think about the atoms involved and what they are doing. That's the point of this. Okay, so why do chemical equations play such an important role in all of this? We've got to be able to, now that we know how to name things, you realize that they get pretty big sometimes in terms of their name. And we've got to figure out a way to say as much as we can in as little space as possible. So by using chemical equations, it tells us a lot. It tells us what we are reacting, the names of the things that are reacting, the charges associated with all the ions that are reacting, and then the states, solid, liquid, aqueous, whatever, and the products that form. Okay, so that tells us a lot. So chemical equations become very important. There's a lot of information associated with them. Okay, so there you go. That's pretty much everything I just said. Okay, it also tells us the relative numbers of the reactant and the product molecules that are required. If I'm taking octane and I'm reacting it with oxygen to do a combustion reaction, how much octane reacts with how much oxygen to give me how much carbon dioxide and how much water? So we cannot answer that if we don't know the chemical equation. Okay, keep this in mind. We already know this. We said we cannot create or destroy matter. Thus, we cannot just, have a certain number of atoms of carbon on this side and all of a sudden just change that number of atoms on the other side of the equation. It can't happen. You've got to account for everything. Okay? So whatever it is that you start with, whatever total mass of reactants you have, that's what your total mass of products has to equal whenever you're all done. Okay. There's methane. Methane is CH4. It's a carbon atom with 4 hydrogen atoms wrapped around the outside of it. Okay? It says methane gas burns to produce carbon dioxide gas and gaseous water. So there you see it. Here's methane right here, CH4. Here's oxygen reacting with it. Here's the products. Okay? Combustion reactions that contain hydrocarbons. Hydrocarbons are things like methane that are made of carbon and hydrogen. You could have 1 carbon, 4 hydrogens. You could have 2 carbons, 6 hydrogens. As long as it's made of carbons and hydrogens, they're called hydrocarbons. They're very flammable, very volatile. So when that happens, you always get this same reaction. The interesting thing is, like in our car, we have 8. We have octane, which means you have a hydrocarbon that is made of 8 carbons. Whenever you burn pure octane, what your automobile produces as a waste product, just from that alone, is carbon dioxide and water. The interesting thing is, glucose is a 6-carbon sugar. Glucose, when consumed by our body, undergoes a similar type of reaction, like your automobile does, sort of like a combustion reaction, that produces, guess what, 2 products, carbon dioxide and water. That's what we breathe out. So our tailpipe and our mouth sort of release the same types of substances. Okay. Like I said before, when something burns, for example, it reacts with oxygen. So let's look at this from a chemical equation perspective. If I'm taking methane, it's in gaseous form. That's natural gas. Okay? The main component of human flatulence as well. So it's extremely flammable. If anyone has any experience with that. If you take methane, okay, and you give it a little spark, realize what a spark does. That's why you have spark plugs in your car, is to initiate this reaction. You draw in air from the outside, bring it into the combustion chambers within your automobile engine. It mixes with gas, so you get an air and gas mixture, so that when you supply a spark, what that spark does is gives enough energy, enough heat and energy to take that oxygen and that methane and cause them to come together to form these products. Okay, and then once it starts, it sort of feeds itself. That's how come you just got to light it once, and then it just kind of keeps going. So you've got methane reacting with oxygen to produce the products of carbon dioxide and water. All right. I want you to pay attention to something as we go through the basics here. Let's say this is a representation of methane Here's, oxygen, okay, two O's stuck together. It's going to give us carbon dioxide and water. I want you to notice something here. As written, does it follow the law of conservation? No. We've got one carbon here, one carbon there. We're all right. We've got four hydrogens here, four hydrogens here. Or, sorry, two hydrogens here. That something happened, right? Two oxygens, three oxygens. How can you explain this? Because this is what happened. These are the products, these are the reactants that react, and these are the products that formed. How can you explain the difference in the number of atoms that you see on the left and the right? Did spontaneously another oxygen just appear out of nowhere? Absolutely not. And likewise, these two hydrogens didn't just disappear. How can we adjust for this? Anybody got any thoughts? Yeah, all that you see up here, what represents is the ingredients. It doesn't tell you how much of each ingredient, right? If you know that you're baking bread, and I should have never started this analogy. I have no idea the ingredients on all this stuff. But, some flour, right? Some eggs. Got to be in there. Cake. I know there's eggs in cake, right? Egg bread. You never had egg bread? Come on. I don't know. You get my point. Take something. You got a microwave dinner, right? Anyways, you got your ingredients. Just because you have some eggs and just because you have some flour doesn't mean you're getting bread, especially if I'm in charge. But what you then have to realize, this gives you the skeleton outline of the ingredients involved and the products that you will get from mixing those ingredients. So what obviously then has to happen here is you've got to tell me how many of these are going to be involved, how many of these, and how many of these will be produced, and how many of those will be produced. And when you start figuring up that, you will see that you can come up with a way where there's the same amount of each atom on both sides of the equation. We call that a balanced equation. Okay, does that make sense? See where I'm going? All right. So this obviously explains the fact that these are not equal on both sides. That's all that shows. All right. So we've got to prove that we're obeying the laws of conservation, we've got to have balanced equations. And if you cannot balance equations, you will absolutely just be so far behind. Because from here on out, in order to do the math, there's a lot of math that are going to be associated with predicting products and how much product forms. If you cannot balance an equation, you're obviously going to get the ratios wrong of how much of this you use and how much of this forms. You get that wrong, there's no way you're getting the right answer. Okay, so you've got to be able to balance these equations. So let's say that I used two oxygens and say two waters were produced. How does this change things? Well, I've got one carbon here, four oxygens here, four oxygen atoms here, four hydrogens there, four hydrogens there. So what that means is I still have the same recipe in terms of what ingredients I used. What I've now clarified is how much of each thing I'm going to use. I'm only going to have one methane. That'll require the reaction of two separate oxygen molecules. I can get one carbon dioxide from this combination. So like you could say these hydrogens fall off of that carbon, and say these two oxygens go to that carbon. The other two would go to, one of those oxygens would go to those two hydrogens, one of them would go to those two hydrogens. You can split it all up, and you get a carbon dioxide, and you could get two water molecules. Now if you arrange it like this, everything works out and everything balances. So you've got to keep that in mind and realize that that's what you're doing when you balance equations. You're trying to make it so that the law of conservation is evident in this reaction. Okay, we already said that. You should already know this as well, what the gaseous, aqueous, liquid, solid, what those designations are. You'll have to include that in equations. Also, keep in mind that, like O2, remember back to our periodic table when we talked about diatomic molecules. Remember it was the rule of sevens. It had N, O, F, Cl, Br, and I. All those were twos, right? Like Br2, I2, O2. What that means is they don't exist as single atom elements. That means if you have a pure sample of them, they're so reactive that they would rather react with themselves than be alone. Okay, so you'd have O2, Br2 molecules floating around, Cl2, and H2 as well. You will find that with the exception of bromine, which is liquid at room temperature, and iodine, which can be solid, I2 can be solid at room temperature. The rest of those diatomic molecules are always going to be gases. So if you see O2, you know it's a gas. If you see H2, you know it's a gas. Chlorine, always a gas. It's Cl2. Okay. Now, again, we've got the numbers. We've got the letters after the formula that we see that indicates our state. We've also got, you'll see a number now in front of each substance. Since there's nothing there, it's sort of like x. You don't put a 1x, you just write x, right? If you're doing variables, same thing. We have an implied 1 here that we don't write. 2 of those, 1 of those, and 2 of those. Now let me ask you this. If you have 2 of those associated with this right here, how many oxygens are right there? Okay, keep that in mind. How many hydrogens are right here? How many oxygens? All right. Now, we obviously, just like in algebra, we call these coefficients. We still do that in chemistry as well. Okay, so coefficient of 1, coefficient 2, so on and so forth. Okay. Okay. Now, you did it in your head because one thing that you can realize is that if I have 2 O2s, and I ask you how many of them were there, you might be able to visualize an O2 and an O2 and realize that with each one of those is 2, so you can see that in your head and get 4 out of that. Or you could realize that the theory behind that makes it easier, is if you have 2 O2, if you multiply that number by that number, obviously it's going to tell you how many of those there are, which will help when you get into more complex types of formulas and that kind of thing. So like, how many of each of those atoms, you know that there's H2O and there's 2 of them, so you can visualize that because it's a small enough molecule to visualize. But what if you get a bigger molecule? You can realize that that 2 means that that goes with everything after it. Okay? Now, if you said 2 H2O, then you can just think of 2 water molecules. If it was a bigger molecule and you had to count all the stuff that was there, it's going to be harder to visualize. So what you can realize is that if I take this number and apply it to every element after it, and I multiply that number by the subscript of whatever elements are after it, then I've got how many of them are there. For example, 2, if it's H with a 2 after it, 2 times 2 is 4. If it's O, 2 times 1 is 2. There's 2 O's. Okay, so that's going to be more important when we get into big types of formulas that you can't visualize in your head as well. Okay, so that's what I mean by that statement there. Okay. Do what? H4O2. I don't understand. Oh, no. Well, because of what we're doing here, if you write a H4O2, that means you actually have one molecule, one chemical that's made of 4 hydrogens and 2 oxygens. That's not what we're saying here. We're actually saying we have 2 different molecules, each of which is an H2 and an H2O. So it has to do with defining the chemical. It's 2 different chemicals you'd be dealing with in that case. Okay. We already know this. I told you this already. Some other things you might want to note if you see these in chemical equations so you don't freak out and not know what it's talking about. There's other symbols that you may see written above the arrow in chemical equations. Just so you know the way that you would read this, like if I had elemental like sodium and chlorine reacting together to form sodium chloride, I would say sodium reacts with chlorine to yield sodium chloride. That's how you would sort of say that, okay, or to produce, but generally to yield. If you see any of these written above the arrow, that means they were used to make this reaction happen. For example, the delta sign generally means change in, right? But in this case, above an arrow in a chemical reaction, it means you used heat. You stuck it on a hot plate, you put a flame underneath it, you did something to increase the temperature to make this reaction happen. If you see HV, that stands for velocity, that stands for Planck's constant, which we're not going to discuss. It has to do with the movement of light particles and that kind of, don't worry about it. Realize if you see this, though, it's in reference to light. Like just the energy from light itself induced this chemical reaction. You know, like those tinted glasses that you can see, people have. You could actually, UV light from the sun has enough energy to when it interacts. These are actually halide compounds. They're made from like silver halides, chlorides, iodides, silver bromides, and those kind of things. There's a complex chemical reaction there that is a real thin coating, so that when UV light shines upon them, it actually changes the molecule shape. It absorbs some energy from UV radiation. When it does, it's a large enough molecule to where it changes its shape to where now it reflects light as opposed to what allows light to pass through it more easily. And in so doing, it makes the lenses a little bit darker, and it keeps light from entering as much. It's kind of cool. But if there's energy associated with wavelength with light, okay? So if light is used in a chemical reaction to cause something to happen, you might see that there. Hydrogen peroxide, H2O2. If you leave it out in the light, guess what happens to it? What do you think it turns into? That's exactly why it explains why it's in a brown bottle. What does it turn into? It's two perfectly harmless substances. Oxygen and water, okay, which are no good at all at killing microorganisms. Okay, so old peroxide doesn't really work very well because H2O2 can be toxic to cells. Yeah, if you leave the cap off too, it'll work the same way. It won't have as much light, but it'll have more environmental reaction. I mean, it can get into the environment. Okay, shock, mechanical shock. You can actually, like, I don't know if nobody in here takes biotech. That's 105 class, but there's a lot of treatments, especially in biological type of chemical settings, to where you can shock something and cause it to just like jumpstart a chemical reaction almost. Electrical, hook it up to a battery like we talked about water. You can take water, run an electrical current through it, and separate out hydrogen and oxygen gas from it. So you would use an electrical current to do that. So there's a lot of different ways to help expedite a chemical reaction. Okay, so how do you write a balanced chemical equation? So the first thing you got to do is figure out what the formula is of the things that you're dealing with. That's the obvious first step. Then you got to count your atoms and make sure that there's the same on both sides. And if there's not, there's a certain series of steps that you can take that makes it a little easier to figure out how you can balance this all out. Okay. One hint that maybe you want to keep in mind is when you're dealing with polyatomic ions, they can give you fits because there's a lot of atoms stuck together there. That when you change the number in front of one, you change it all after that. You end up messing with all the numbers present. Sometimes it's easier to treat, instead of looking at each atom involved with the polyatomic ion, sometimes it's easier to look at it as an entire unit and keep track of it as an entire unit. I'll show you what I mean when I give you an example. Then you just got to start somewhere. You got to start with an element. I'll give you some hints as to what you should start with and what you shouldn't start with. Okay, but you just want to start with something and work and start working, and it's a process. At first, it's going to take you a while to get the hang of this, but then you'll get better and better. At first, it may take you a long time to balance these equations, but you're going to have to get good at it because you don't want to come test time, spend all your time just trying to balance an equation and then never get the chance to answer the question associated with it. Okay? Now, another thing that you want to do is I say leave elements that are free elements somewhere in the equation until last. What that means is, like for example, if you have oxygen reacting in your equation, what you've got to realize is if you put a number in front of O2, like 2O2, 3O2, you are only affecting oxygen and you're not affecting the count of any other atoms in that equation. So what you want to do is use that to your advantage and realize that if you save that until last, you can put whatever number you need in front of that to make it work. Okay? You don't want to start there. That's a bad place to start. You want to end there because you can put whatever you need there. Okay? All right, I'll show you this. This is an explanation. I'm going to show you through examples how to do this. You can read back through this explanation yourself. Okay? I'm not going to read through all of this without showing you an example. So let's take a look at this. When magnesium metal burns in air, it produces a white powdery compound, which is magnesium oxide. So here's the equation for that. Solid magnesium react with gaseous oxygen to produce solid magnesium oxide. Okay? All right. Is this equation balanced? No. This one's an easy one to balance. Okay? They get harder, I assure you. But let's start here. Magnesium and oxygen. I've got one magnesium, one magnesium. Agreed? I've got two oxygens here, one oxygen here. Now, in this case, you've got these two things that are independent. They're not hooked on with anything else. So whatever number I stick in front of magnesium, all I change is the number of magnesiums. Whatever number I stick in front of oxygen, all I change is the number of oxygens. However, if I put a number in front of here, guess what I change? I change both magnesium and oxygen. So what I want to do is, for future use, so that you keep this in mind, if I have something out here that's by itself, I want to save that until last. That's what I want to do. In this case, I have two things by themselves. Most of the time, it won't be that easy. You'll have maybe one thing by itself and this hooked on with like magnesium chloride or something else. Okay, now in this case, it would make sense that since my magnesiums are already balanced, I need to focus on my oxygens. So what would I do? What could I do in my first step in an attempt to balance this equation? Anybody? Right, put a 2 in front of the magnesium oxide. Now, if I put a 2 in front of the magnesium oxide, is the equation balanced? No. Then I'd have to take and put a 2 over here. And if I put a 2 over here, it would be balanced. Let's take a look. We count the numbers. Okay, in this case, we don't have any polyatomic ions, so we won't worry about it. Okay, I got 1 magnesium on both sides, 2 oxygens over there, 1 oxygen over here. We already said that. So we pick an element to balance. Since the magnesiums are already balanced, it wouldn't make much sense to start messing with those. So we start messing with oxygen. All right, you said, since there's 2 over here and 1 over here, let's multiply this side by 2. Okay? If I do that, I get this. Now when I get this, I've got to look and realize, okay, now I have 2 oxygens. Now I got 2 oxygens over here. I'm good. I've got 2 magnesiums. However, I've only got 1 magnesium here, and your answer was to put a 2 in front of that magnesium. When you do that, you get this. Okay? Now is it balanced? Yep, that's it. Okay, that's all you got to do to balance these equations. You just got to make sure that the law of conservation of matter holds true. You got to make sure there's the same number of atoms on both sides. Okay? Okay, let's take a look at this. It says, I've got ammonia gas reacting with oxygen gas to produce gaseous nitrogen monoxide and gaseous water. So guess what you've got to be able to do? Understand what I mean by these. So you got to know how to name things. You got to know how to write things. How do I write ammonia? NH4 positive is ammonium, the ion. NH3. What state of matter is it usually in? Gas, so NH3 with a little g after it, right? I'm reacting that with oxygen gas, so how would I write that? O2 negative? No, this is, O2 just by itself. There's no ions here. I'm just saying oxygen gas. That means they've hooked together to eliminate any charge. That's what they've done, okay? So we've got O2 with a little g for gaseous. I'm telling you that you're making nitrogen monoxide. What's the formula for that? NO. Okay, all the nitrogen and oxygen compounds are going to be gaseous. Okay, so nitrogen monoxide and gaseous water, which is H2O. That's an easy one. So now you know the formula for everything. We got to write it out in skeleton form. Okay, we did that already. We've already figured this much out. And what you've got to keep in mind is what I've pointed out here is this is why now you have to know your diatomic molecules. Because if I say oxygen, you can't just write O. If you just write O, you will not get this balanced correctly. Okay, it won't work. You might be able to balance it, but it will be incorrect so that when you try to answer any math questions associated with it, it will be wrong. You won't be able to use the right ratios. So you've got to know that, that's a common name, and it means dihydrogen monoxide is what water actually would be called, but it's stupid to call it that. So just it's water. All right. So, knowing what we know, now we can make this happen. Okay, that's the formula, or the formulas for this equation. Is it balanced? Well, let's take a look. We've got to break it down. Okay, look at the ends. Are the ends balanced? Are the O's balanced? Are the hydrogens balanced? No. Okay, so probably what do you want to try to save till last in this equation? The oxygen. Now, it's going to be a little tricky because it's O2 and not just an O by itself. So what you have to multiply by may be kind of weird, but nonetheless, we can still control it. So let's hold off on it. Let's look at what we've got here. What we want to try to do is to do something. Since our N's are already balanced and our O's are already balanced, we're obviously going to want to mess with the hydrogens. Okay? Now, in this case, there's not an option. We can't just multiply one side by something and not do anything to the other side. It won't work. Okay? Like if I put a 2 in front of the H2O, I've got 4 hydrogens and still only 3 over here. So guess what you're searching for here? Least common multiple. Bring back those math terms now. Okay? You've got 2 hydrogens here, 3 hydrogens there, right? What's the least common multiple of 2 and 3? 6. So we want to make it to where there's 6 hydrogens on both sides. So to do that, I'd put a what over here? Okay, and I'd put, now what have I just done? Created a mess is what I've done, because now I've changed the number of nitrogens that I have, and I've changed the number of oxygens that I have. So let's take it baby steps. Let's write down what we've got so far. Okay? But you're right, though, that is a step that you have to take. Well, we have to do that first. Okay. So here was our count. We've already established that. And we decided to start with H. I'm just skipping all the stuff that we already discussed. So we decided to do this, multiply that side by 2, that side by 3 in terms of our H's, and as such, we have this so far. Okay? We have 2 ammonias plus an oxygen plus nitrogen yields a nitrogen monoxide and 3 waters. Okay? Now, like we said, we are not balanced now. Our H's are balanced, right? But not our nitrogen and not our oxygen. Now, what we probably want to do is, like I said, save our oxygen until last, because we can manipulate it when we do that. So let's then take the next logical step would be to focus on the nitrogen. What can I put in front of this nitrogen to balance things out? If I put a 2 there, I've balanced my nitrogens and my hydrogens, but now I've got 2 oxygens here, 3 there. That's 5 oxygens over here, and only 2 over here. Now let's see how that's going to play out. Okay? Let's skip all the stuff in the head that we just did. This is what you just told me. Blah, blah, blah. All right, here's where we are. Okay, this is where we got to. We are at the point where we know that we put a 2 here, and we put a 3 over here because we had to balance our H's. We used at least common multiple of 6. When we did that, we changed our counts of N and O. Since O is by itself, we left it till last. Okay? And then we messed with our N's. It was 2 here. There was only 1 there to start with, so we put a 2 in front of that. Okay, so now everything's balanced. The only thing that's not balanced is oxygen. Now, use your noggin a little bit. If I have on the left side, right now I can manipulate this. I have 2 oxygens as listed, but on the right side I have 5 oxygens. See how I got that? Okay, 3 oxygens here, 2 oxygens there. I have 5 oxygens. Is there a number that I can multiply by 2 to get 5? What? Yeah, be careful though. Be careful. What times 2 equals 5? In other words, what's 5 divided by 2? 2.5. If I take I know this is crazy, but think about it. If I take 2.5 O2s, assuming you could do that, if I take 2.5 oxygens, how many oxygens would there be? 5. If I took 2.5 O2s, remember I take this number times that number, right? So 2.5 times 2 would be 5. If I did that, everything would be balanced. Now, it seems ridiculous because how can you have a half of an oxygen molecule? Well, you can't. Okay, yes, both of you, and I'll show you. Okay, let's put a 2.5 in front of that. Okay, to balance this equation, here's what we got: 2, 2.5, which is a red flag because it looks stupid. 2 and 3. Okay, as written, everything balances out, but we don't want decimals and we don't want fractions in this class. Okay, we don't want that to appear in our chemical formula. So what can we do? There's an easy way to clear a fraction and to clear a decimal. In this case, what can you do? That's right. Double everything like you did back with empirical formula stuff, right? If we double everything, this goes to 4, this goes to 5, this goes to 4, this goes to 6, and you count them all up and everything's balanced. Easy enough, isn't it? Sure it is. Piece of cake. All right. So that's what you would get. You might have had to have multiplied by 3. You might have had to have multiplied by 4. It just depends on what decimal number you would have gotten there. Okay? Just like we did with empirical formula stuff. So there you go. Huh? No, if that was like a 2.33, you would have had to have tripled it to get a number closest to the whole number that you can. If it was a 2.25, you would have had to have quadrupled it to get that whole number. Okay? You'll find that most of the time you won't have to do this. Where this is going to be a problem is whenever you see oxygen in your equation. or any diatomic molecule, usually oxygen. Most of the time, it won't be that complicated. But I show you this one because if you can do this one, you can do all of them. Okay. I should be able to go through this rather quickly because I've already talked to you about aqueous solutions and what happens in them when we did our little pre-lab lecture over a precipitate lab that we did. You should know what an aqueous solution is. It's when ions are immersed and floating around in a sample of water. We call that a solution. We symbolize it AQ for aqueous. Remind me why aqueous is different than liquid. Okay. Yes and yes. The aqueous means something is dissolved in water. Liquid means it's just that pure substance. Okay, like liquid water means only water is present. Liquid iron means there's nothing but molten iron present. Okay, aqueous, there's something dissolved in it. Okay, now realize that by putting something, why this is important in what we call wet chemistry. Okay, by putting something in aqueous solutions, we make reactions happen a lot more easily. Because if you just imagine taking sodium and taking a lump of sodium and putting it in a container and filling it with chlorine gas and letting it swirl around, you can imagine that there's going to be not a whole lot of interaction happening there. If you take two different types of reaction or two different types of solids and try to cram them together like Play-Doh and mix them up, you're not going to get the best possible interaction of all the atoms, right? Because some of them are going to be stuck behind other ones and all that. If you can put them in aqueous solution and spread them all out and give them all a chance to interact with each other, you're going to increase the rate and the productivity of that chemical reaction. Okay. Let's see. Don't worry about that right now. I discussed most of what we need to know in lab already. So here we have a sample of like sodium chloride, aqueous solution, silver nitrate aqueous solution, and we also know now what can happen if I take these two things and pour them together into a container, right? You could get new pairs. What you have to look at is whether or not then when these things come together, is it going to form something that's insoluble or form something that remains soluble? Okay. I told you in the last lab if a precipitate formed what it was. The difference between that and where we're going now is you're going to tell me what precipitate will form. Okay? And I'll show you a table on how to predict that. So in this case, we've got dissociation. You took solid salt, put it in, it dissolves. All these things are what's called dissociated. They're floating around. Now, not all ionic compounds are going to be soluble in water. Okay? Sometimes you will not be able to take some sort of sulfate or hydroxide material that has those ions in it and throw it in water and expect it to dissolve. Sometimes it won't. It depends on the nature of that chemical compound and whether or not it will dissolve. Now, another thing to keep in mind when we're dealing with polyatomic ions, and this is sort of already implied, you probably already picked this up, but the polyatomic ions themselves, like look at silver nitrate, AgNO3. These N's and these oxygens do not separate from one another. They are a functional unit. They are one ion. They're just four atoms that make up that ion. Okay? So keep that in mind. When a polyatomic ion dissociates, the polyatomic ion itself remains intact. It's one of the ions now floating around. Okay? So that shows you there's potassium iodide dissociating. Calcium sulfate, sorry, it looks like copper 2 sulfate. Copper 2 sulfate, when it dissociates, will give you not copper, not sulfur, not oxygen, but instead copper 2 ions and actual sulfate ions that are present. Okay, so what can happen when you mix those two things together? Now both of those, if you look at this page, these are both soluble. Okay? This is sort of a bluish color. It would make the water blue. This is clear. You put these things together, this by itself is soluble. It'll stay like a solution. No precipitate will form. Here, this is the same way, but when you mix them together, you stir up the pot a little bit. What can happen? The potassium now, formerly bonded with the iodide, could come in contact with sulfate. Well, in this case, it just so happens that potassium sulfate is soluble in water, so it will not form a precipitate. That's one possible combination, but it won't turn into anything. Okay. What are electrolytes? Because they're directly associated with what we were just talking about. You've heard of this before, like you heard Gatorade, and it's full of electrolytes and all that kind of stuff. Gatorade, of course, what's the history of that? That's right. They had the commercial not too long ago with the actual chemists on there. Chemists from the University of Florida invented Gatorade, hence the name. So, electrolytes are ions that are dissolved in solutions. Electrolytes are solutions, I guess, that have the ability to transfer electricity, okay, through them. Generally, the more ions that are dissolved in a solution, the better it is at conducting electricity. That's why if you're sitting in a bath of distilled water and lightning strikes, you're nowhere near as in much danger as if you were sitting in a giant tub of salt water. Okay, because the more salt particles there are, the more sodium and chloride ions are present, the better those atoms can take electrons and shovel them back and forth between each other and propagate an electrical charge. Okay. So obviously dissolved ions then, as we were talking about, create what's called electrolytic solutions, solutions that have the ability to transfer electricity and run a current through them. Like in pure water, if you had a battery and you created a circuit, now normally if this was tied together and this was one circuit, that bulb would light. Okay? Now if you broke this and tried to use this solution as part of your circuitry, in the case of pure water, you would see that it's such a weak electrolyte, it does so poorly at receiving this electrical charge and then dissipating that electrical charge. It's very bad at it. It cannot complete that circuit enough to light that bulb. However, if you take a salt water solution, you may not get as brightly lit of a bulb. You've lost some of your electricity, but through that circuit, those sodium and chloride ions have the ability to transfer electrons through one another and propagate that electrical current all the way back through to the point where it can actually, this solution can be part of the current. I don't think we'll get into it too much in this class, but one of the things I discuss in Chem 2 is like voltaic cells and how batteries work, and car batteries and wet batteries versus dry batteries and all that kind of stuff. So it's kind of interesting. But all right. Now some things, just because there's something dissolved in water doesn't mean it's going to conduct electricity. Because what you have to have dissolved in water are things with charges. Okay? Things that can have a positive and a negative associated with them, so that allows electricity to flow. In the case of like sugar water, sugar is a very, very, what's called a nonpolar compound. In other words, it's covalently all held together. It's a bunch of C's, H's, and O's, but there's no charges associated with them. They're all tightly held together. So as such, there's nothing about them chemically that would be attracted to other places in terms of electrical charge. There's no positives to pass on something to a negative and vice versa. So in this situation, that's a very weak, if not non-electrolyte solution. It's not going to transmit that electricity very well. Electricity meaning just the movement of electrons. Electrons travel from one place to another, and when they do get passed on and travel, that's electrical current. Okay, so you got strong electrolytes and weak electrolytes and even non-electrolytes. Okay, so in a strong electrolyte solution, you've got everything dissociated and falling apart. In a non-electrolyte, you've got nothing dissociated and falling apart to form ions. In a weak electrolyte, you've got something that mostly stays together, but some of them separate, some of them fall apart. And that would be a weak electrolyte solution. Okay, obviously salts are all going to be any salt, which is an ionic compound containing a metal that can be soluble in water. That's what a salt is. All the salts will be strong electrolytes, or I guess at least electrolytes, not always strong. But acids can be electrolytes because acids are sort of like ionic compounds, except they don't have a metal with them. Instead, they have a hydrogen ion. So when they fall apart, they have ions floating around, so they can be an electrolytic solution. Acids have a sour taste. I'll talk more about that in the very last chapter, but the German word for acid is actually sour, like sauerkraut. They tend to dissolve metals, react with metals, that kind of stuff. They can go into solution, turn them away from being a solid and turn it into solution. Bases can be electrolytes. What bases usually consist of is like one of the alkali or alkaline earth metals. That's how they got their name. The word alkali or alkaline means basic in nature. So what you get is like what's called metal hydroxides, like lithium hydroxide, sodium hydroxide, that kind of stuff. Those are all bases, and they ionize into hydroxide ions and then the metal ions, and they float around, and they can create electrolyte solutions. Okay. It says, when will a salt dissolve? Obviously, when we're talking about soluble, we mean that. It will dissolve. Okay? If you put it in a liquid and it dissolves, we say it's soluble. For example, sodium chloride is soluble in water, but silver chloride is not. Insoluble means like if you take silver chloride in solid form, drop it into water, you're just going to see silver chloride sitting in the water. Probably not going to dissolve very much. So we call that insoluble. Okay? Now, don't get me wrong. There's no way to prevent some of these ions from separating and just a few of them being floating around in this water. There's going to be some. But the amount is going to be so negligible and so small that you'll never even notice it change from what's here. So we consider that insoluble. Okay? Now, it says predicting whether a compound will dissolve in water is not easy. It is for you, but for the chemists who had to figure all this out, it's not, because mostly what it is trial and error. It's most of let's mix it together and see if it'll dissolve. And then let's keep track of all of our results so that we can make a table in chemistry books so people never have to do this again. Okay? And that's where these tables are going to come in that I'm going to show you. I need you to get familiar with this. I will provide this table for you, but you'll be using it to the point where you probably memorize it as you're doing the homework and that kind of stuff. Notice how this is broken down. It says, compounds that contain the following ions are generally soluble, and if there are any exceptions, they're listed over here. So in other words, no matter what you have, if lithium, sodium, potassium, or ammonium is your cation, it could be ammonium nitrate, ammonium chloride, sodium chloride, lithium nitrate, whatever, doesn't matter. If these cations are present, they fall off so easily that they are always soluble in water. Whatever compound they make will always be soluble in water. Okay? Now, if you take some of this and keep in mind and start looking at some of the chemicals that I pick to use in lab, and you will see that I use a lot of nitrates, I use a lot of chlorides, because these things are very soluble in water and they release ions very well to float around to cause reactions to occur. Okay, there are no exceptions to that. Anything with this anion, the acetate ion, or the nitrate ion, no matter what the cation is, if either one of these two anions are present, that compound will be soluble. It will dissolve in water. Okay? It is very, very hard, very difficult to precipitate and get a compound containing a solid of these things. Now, I know you might think, well, I pour salt on my food all the time. Well, yeah, that's already been crystallized. It's been dried out and it's been solidified. I'm talking about if you have a mixture and you already have aqueous solutions, good luck in separating the sodium, the potassium, the lithium out from that solution. Because one of the easiest ways to separate things out is to treat it with something that will form precipitate with. And you can filter it out, and then you know that your precipitate is like that ion with another ion, like lead nitrate or sodium, or in that case sodium won't work, but silver chloride, whatever. And then you can do something else to separate those ions out. But what you got to realize is with these guys, it's incredibly hard to, once they go into aqueous solution, and you start mixing stuff together, it's incredibly hard to get them back into solid form. Anyways, usually anything that has chloride, bromide, and iodide ions with it as its anion are almost always going to be soluble, easily dissolved in water. There are some exceptions. Lead 2, mercury 2, silver. If you have any of those, like silver chloride, silver bromide, silver iodide, or whatever, those are the exceptions. Those will be insoluble. They will not dissolve in water. Okay? Sulfates are generally always soluble in water as well. The only exceptions being calcium, strontium, barium, and lead 2. Okay? Those sulfates are not soluble. So you'll get used to that. You need to, when I ask you any questions, you refer back to that and you can follow it. So if I ask you, for example, whenever you are mixing, think back to the lab, you mixed silver nitrate. It was an aqueous solution, right? Nitrate, no exceptions. It's not a solid. If silver nitrate was insoluble, you wouldn't have it in aqueous solution. It would just be a dry powder. Okay, so silver nitrate, and you reacted that with sodium chloride. Sodium chloride. Okay, sodium, no exceptions, always aqueous solution. So you've got sodium chloride, silver nitrate. Two things can happen. Sodium and nitrate can come together, or silver and chloride can come together. How do you know now what your precipitate is? Well, if it's sodium and nitrate, you got to look. Is that possible? No, it's not. There's no way that could have been your precipitate. So if you got a precipitate, it had to have been silver chloride. Is that possible? Yes, it is. So you start using this table to start figuring out the other side of chemical reactions. You start figuring out how to tell me what reaction occurred and explaining to me what just happened based upon how you use what's called these solubility rules. Okay? One more table here. Looking at the anion side of things. If you remember the part D in that experiment, you did the pretty colors. You did like nickel hydroxide and cobalt hydroxides and those kind of things. They had all those colors. They were very insoluble, right, when you mix them together. You took sodium hydroxide and you mixed them with aqueous solutions containing certain metals. Well, when you bring in hydroxide ions, like from sodium hydroxide, and they mix with most metals, they form insoluble products. So this table says insoluble. If something is a hydroxide, some sort of hydroxide compound, it's probably going to be insoluble unless it is one of these. Okay? Unless it's lithium, sodium, potassium, or ammonium. And if it happens to be calcium, strontium, or barium, we call that slightly soluble because it's sort of in between soluble and insoluble. So you just have to know how to use this table. Okay? Sulfides, things that are bonded with sulfur atoms, mostly always insoluble unless it's hooked with some of these. Then they could be soluble. Same thing down here. Carbonates and phosphates, usually always insoluble unless they're bonded with these. Okay? So know how to use that table. Know what it means, what it stands for. So let's skip this. That's what I just said. And let's look. Okay, don't cheat. Only look at your solubility table. Potassium hydroxide, soluble or insoluble? Soluble. Anything that's potassium is soluble, right? There's no exceptions. Silver bromide. Insoluble. Calcium chloride. Soluble. Lead 2 nitrate. What does it say about nitrates?
Soluble.
Soluble. Is there any exceptions to nitrates? No. There should not be any exceptions to nitrates. So is it soluble or insoluble? Soluble. So that's not going to be an answer to any of your precipitates, ever. Lead, you tell me, what's the name of this? Huh? Lead 2 sulfate, right? SO4 2 negative. Pb had to be a 2 positive to balance it out. Lead 2 sulfate. Lead 2 sulfate, soluble or insoluble? Insoluble. Okay, good. Easy enough. Looks like what we got here, a little iron hydroxide reaction. It looks like formation of a little iron hydroxide here. Maybe that's a little iron chloride. You only need a little orange, a little sodium hydroxide. I'm guessing. Okay, we've discussed precipitate reactions already, so shouldn't be too big of a deal. We did this in lab. So let's skip over the little intro. Here's one of the reactions that you did in lab, right? We had lead 2 nitrate. You brought in some potassium iodide the second they came in contact. We know now from our solubility rules that one of the options was potassium and nitrate, but that's a double whammy because all nitrates are soluble and all potassium compounds are soluble, so that's for sure not going to be insoluble. The only other option was this I and the PBs, lead 2 iodide, and in that case, I know it probably didn't list it on there, on that sheet, but that would be an insoluble compound. So that explains what we saw. There's a balanced equation for what we saw. Now, I know that I had you give me net ionic equations because those are easier to balance because you just have ions to count and to keep track of. I didn't have you write and balance the entire full equation because that's a little bit more challenging. You can do it now, but I hadn't talked about it yet, so I didn't require you to do that. So what you should be able to do now is if I ask you, you're mixing two things together, you should be able to, okay, first of all, write down the formulas for all the things that you're mixing together. Write down the state of matter in which you're going to find it. Is it a gas, solid, liquid, or aqueous solution? When these two things react, what possibilities exist on the other side of the equation? You thus can now fill in what's missing. If this was not there, you should be able to tell me what will be there. If you mix these two things together, you've got lead 2 ions that could swap partners and go with iodide and make PbI2. So you could write that over there. You don't know if it's a solid yet, but you're going to check here in a second. Then you could have potassium ions and nitrate ions coming together to make a potassium nitrate molecule. That's one possibility, so you write it over there. Well, then what you would do is balance the equation, okay? Make sure everything's balanced, and then figure out what states of matter go with this. We obviously know this was aqueous and aqueous. I told you that, and you can look up on the solubility chart and find out. How do I know which one of these explains which one of these is going to be a solid? Because one of them has to be. Okay? Look at your chart. Find out what reacted with what. In this case, you know, even if PbI2 is not on that chart, one thing that you do know is that that can't be it. Okay? Do a process of elimination. That can't be the insoluble compound. That means that has to be. So you write that as aqueous, because really what that is telling me is not that these things are hooked together. It shows me the possibility that they could be hooked together. In actuality, by putting that aqueous after it, what you are telling me is they are floating around in solution separate from one another. Okay? You've grouped them together for ease and to explain what's going on. PbI2, however, is stuck together, and you indicate that by putting that solid sign after it. Okay? All right. So there's a visual of what's happening. And the PbI2 is actually the solid that forms as a result of this. Bless you. Let it out, man. Let it out. All right. What about this one? If you take potassium iodide and sodium chloride and you mix them together, will anything happen? You should be able to tell me. Now, the picture tells you, obviously, that nothing's happening, right? You can tell by watching. But you should be able to predict before you ever do anything as to whether or not something will happen. Let's rearrange this equation. These are obviously aqueous solutions you're mixing together. What's your new possibility? Well, this K and that Cl could come together to make KCl. NaI come together to make NaI. Now, if that's the case, balance the equation. Looks like it's all already balanced the way it is, so you're in good shape. Don't take that for granted. Don't assume from here on out I'm just going to give you balanced equations, because I won't. Now, at this point, you've got to figure out how to write this. Well, you saw no precipitate form, right? So there's no solids. Now, you don't know if it could be a liquid that formed. Maybe this was actually a liquid that in which you would have to account for that. You would have to write liquid as opposed to aqueous. So we still have to check our solubility table to make sure. Okay? So in this case, obviously no bubbles, no gas or whatever. So we've got two things here that we're dealing with. How do we write those? What do we know those are? They're not solids. Look at your table. You'll find that that is extremely soluble. All potassium compounds, all sodium compounds, soluble. Nothing happened. So what you get here is all it is a big soup of those same ions all floating around without any interaction. Okay? So there will be no reactions. All the ions are still present. Indicate that with aqueous outside of it.
If it's liquid, you know the difference between aqueous and liquid, like in that it would be a liquid if it's a precipitate.
Don't worry about the liquid. That'll never be an issue. I should have never said it after I said it, but instead of going back over it again, then I just hope that it will get swept under the rug. But it didn't. So don't worry about it. Just ignore that. The only thing you care about right now, all I'm going to ask about is solids, precipitates. That's it. Is it insoluble or soluble? Don't worry about the rest. Okay, what's that? You're fine.
Back on the other one, where you have the reaction in the product. How do you know the potassium goes with the iodide?
Okay.
Is it first and last, and then?
Let me go back. This,
You know what I mean?
We'll stop with this one. So pay attention. Here's the question. How do I know if I'm mixing potassium iodide and sodium chloride together? How do I know that these are my possible combinations? That's right. Look at your charges that you have. Obviously, you're not going to write the same thing. You're not going to write Ki again over here. The whole point is to have something different on this side. What are your choices? You have a K. When this dissociates in aqueous solution, what charge do you have? You have a K positive, right? So a positive charge. This is a negative charge. That's a positive charge. That's a negative charge. So if you're going to give this guy a new partner, what is the only thing that it can partner with? A negative charge, which would be this chloride. Okay? The only thing that this guy can partner with is a positive charge, which would be that sodium over there. Okay?